Thank you for coming. Tell us about yourself.
My name's Steffen Cruz. I am coming from industry. I run a research lab called Macrocosmos. I'm here at NeurIPS to, meet people that work in my field, hopefully meet my heroes in the fields as well. That's always nice to stumble into some of the great godfathers of the stuff. And yeah, more than anything, to just sort of absorb the current thinking. It's really hard to come to a place where you can get just such a big download of like the bleeding edge of the field. So being here is really nice. Everyone is super sharp and really, at the most advanced state of the field right now, which is a great time.
Which are these heroes?
I met Richard Sutton. I'm very proud of it. I went to his keynote speech and I asked a question, and then afterwards I followed up. I met him outside and we had a quick chat about how we can operationalize the idea of play in reinforcement learning systems, which I think is a delightful topic.
It's super fun. Mm-hmm. What does Macrocosmos do?
So we do a few things, but our primary focus is our work on distributed training. So our thesis is to provide a very capital efficient training compute layer where people can train large models, but instead of using a single data center, sort of floor to ceiling racks of GPUs, empowering them to be able to do it actually using compute that's distributed around the world. So that's our vision. We've been working on this for about 7 months. Macrocosmos is about 2 years old. And we've explored a lot of sort of distributed system designs in that time. We've trained some models. We've also worked quite a lot at the intersection of AI and game theory, which is quite interesting too.
What's the hardest part of solving that problem?
The hardest part of actually getting distributed training to work is the fact that you have this massive inefficiency because you're communicating so much data over the open internet. So comparing that to what happens in a data center when you've got very high bandwidth interconnects that are transferring data, it's about 1,000 times slower to do it over the open internet. And so our research is really oriented around sharing less data less often, is what we say. And the idea of this is basically trying to make up for the difference of all that inefficiency. And it's very much an open research field. It's something that we're making progress on. There's other teams in the space as well. It's generally called distributed training, or there's a bunch of teams that have been here this week from DeepMind and some Web3 teams that are all trying to sort of do the same thing. And it's moving forward at actually a surprisingly fast speed, which is great.
Awesome. How did you come across this problem?
I came across this problem a couple years ago. I stumbled across a project called Bittensor. Bittensor is a Web3 project that aims to democratize AI by allowing participants around the world to coordinate their efforts and contribute their knowledge and expertise. So it's sort of like an open source, democratized version of a university or something like that. Yeah, the individuals that created Bittensor are really passionate about exactly this problem. And the more we talked about it, the more I realized it was just a really elegant problem from an engineering point of view, and something that would bring a huge amount of benefit to humanity, in my opinion. I think in the future state of the world, we're not just going to have one or two monolithic models. It's not going to be one model to rule them all. It's actually going to be many, many models that are specialized, and different enterprises, different countries will want to have their own models trained on their data. And the problem is it's extremely capital intensive, and it's also something that has a very high barrier to entry in terms of specialization and skill. So I just see this as a really neat engineering problem that brings an enormous amount of benefit, and also is much more sustainable because you don't have to suck all of the energy from one area of one place where a data center is. You can actually balance it out around the world and distribute it, which is inherently more efficient and also more cost efficient.
What are you looking forward to in distributed learning for 2026?
I think a symbolic victory and a great step forward would be producing models that are good in comparison to frontier models. I think it's one thing to create tier 2 models using a novel architecture, but it's another thing to say this can go toe to toe. I hope that we start seeing that. It's probably not going to be the 1 trillion parameter models next year, but maybe mid-sized models, we might find that teams are able to really get the recipe right, and there's a lot of work that goes into that. But yeah, ultimately, models are only as good as the use they give people, and no one wants to play with the second best model. Everyone wants best models, and I think distributed training and distributed AI needs to leave its mark there. And hopefully that will happen next year.
How has it been talking to researchers who use compute about your work?
It's a mixture of, I think, curiosity and bewilderment. So the current zeitgeist right now is very much that training is really, really hard, even when you're not doing it distributed. Just using a single data center and everything behaves nicely, it's already really hard. I mean, there's a reason why it's kind of like the holy grail right now for the world is to create these more powerful systems. So they look at me with shock and horror when I say we're going to do that over the internet in a noisy environment where compute nodes can pop in and out of the network. It's not even that it's synchronous and the entire network is static over time, but it's actually unreliable nodes can join and they can leave, and this is just a really noisy, churning system. So for them, it's fascinating. I think they see that this is a really ambitious and potentially a very valuable and powerful technology, but I think that they also see that as, wow, you've really picked a hard problem. that's a hill that you don't want to, you don't want to die on that hill.
Those are the best problems.
Yeah, that's what I think too. Yeah.
Awesome. What are some predictions you have for the future of AI?
Wow. I'm not sure if I have any hot takes right now. I think taking a lesson from science. So I'm a physicist. My background is subatomic physics, which is what I studied for about 10 years. So physics is a much slower machine. Physics evolves very, very slowly. New data is collected, new theories are developed, they're reconciled. But it also really sets the bar for a coherent, self-consistent body of knowledge. And I think where we are in AI right now is really scrappy. It's like there's very few deeply theoretically sound reasons why things even work. And that means that there's a lot of opportunity to tighten up our understanding of this and formalize it and turn it into an elegant mathematical language. Right now, we're just throwing so much compute, and we found a suitably general architecture, the transformer, which works well and scales well, and that's brilliant. But I don't think that's where the book stops. I think that there's going to be so much more progress that we make. Transformers are incredibly expressive, and they can represent all kinds of things, which leads to these powerful models. But at the same time, I still think we're brute forcing our way through the problem, where there's probably much neater ways of doing it that are tidier, and that would translate into compute efficiency, things that can continue to learn after they've been trained in the initial stage. And I think that's kind of what everybody wants. But right now we're at this point where everyone's sort of in a race to the bottom to make the existing paradigm and just stretch it to its limits.
So you're very skeptical about scaling.
I think the scaling will continue. I don't think we're at risk of this stagnating next year or anything like that. Post-training has really come into its own right now. I believe that there's more compute thrown into post-training than pre-training now, which is actually a super interesting tipping point for the field. And with RL environments and cleverer ways to actually orient these models to specialize in all these different valuable use cases, I think that we'll continue to see progress for a few more years, even with exactly what we have right now. Whether the models will keep getting bigger in the way they have is an interesting question, because that feeds into things like the economics of these massive build-outs of data centers, which are, I think they're already approaching the size of Manhattan. In a couple of years, we're going to be talking about small nation states. You pave over all of Denmark in order to build your data center, and at some point that's just untenable. So I think we will see a lot of progress, but I think the evolutionary pressure to make progress on the algorithms again will come back when we realize that it's just too expensive to scale this recipe too much further.
Got it. Great. Any final thoughts?
I guess just thank you very much for inviting me here to talk, and it's been a great week so far, and this is the last day, and looking forward to seeing some friends for dinner.
Awesome. Thank you so much.
Yeah.
Thanks, Steffen.
Thank you.